We start the afternoon session with very interesting presentation from Dr. Gary Consolazio, advances in bridge design vessel impact loading from equivalent static to efficient dynamic analysis. I had the pleasure of working with Gary for many, many years. I was the editor of journal, and Gary was associate editor, particularly in charge for all the papers related to ship and vessel impact. He has, been working on this for many, many years. As you can see, he's the recipient of 2003 TRB KB Woods Outstanding Paper Award for his work on vessel pier soil interaction during barge impacts. But overall, he has done, pioneering work on barge vessel impact on bridge piers, full scale experiments, and a lot of his work has impacted the ASTO code that we currently use. So with that, I will invite Gary to make his presentation.
Okay.
Scott, please share the screen and give Gary his.
And just to confirm, the audio is being shared, I think, with this.
Yes.
Okay.
I think yes.
Okay. Great.
I can hear you. You are good.
All right.
Yes, it will be.
Okay.
Okay. Thank you. All right. Well, thank you for the introduction, Anil. So what I hope to do with the next 25 minutes or so is talk about how we can use both advanced finite element simulation as well as full-scale and reduced-scale experimental testing to transition the process of designing bridges from an equivalent static approach to what I'll refer to as an efficient dynamic approach. Okay, so to get started here, I am a professor at the University of Florida. Been working with the Florida Department of Transportation for about 25 years on various aspects of bridge design here in the state of Florida. A vessel collision design is definitely a focus of ours, as has been pointed out previously, that 1980 Sunshine Skyway collapse that was a result of a ship impact, set into motion a lot of changes in bridge design for vessel collision loading. A little lesser known is the 1989 barge impact incident on the Pensacola Bay Bridge that caused a near collapse. And we've had more recent incidents in this as well. What's worth pointing out is that in Florida, we have over 1,500 miles of navigable waterways. Some of those are coastal, some of those are inland. Some of them are deep, as in Tampa Bay, that can accommodate deep shipping traffic, large ships, as we've been talking about today. But in Florida, we have a large number of shallow waterways that are navigable by barge traffic. And so barge traffic presents a particular risk to our bridges. And so we've spent a good deal of effort and focus on barge impact loading. And so you're going to hear a lot about that in this presentation. I will say that although I'm talking almost exclusively about barge impact, the concepts apply equally well to large ship impact as well. So some of the tools that we use in the state of Florida for bridge design include obviously the AASHTO provisions for vessel collision design and highway bridges. They include results from research that's been funded, again, over many years, 25, 30 years at least, by the Florida Department of Transportation and conducted here at the University of Florida. And also, I'll point out that we at the University of Florida have the Bridge Software Institute, where we produce software which is used by engineers to assess bridge vulnerability to vessel collision design. And so those are among some of the tools that are used for bridge design here in Florida. Now, I mentioned I'm going to be talking about how we advance from equivalent static approaches for design to efficient dynamic approaches. And some of the things I'll be touching on as I go through the presentation are outlined here. That is the use of advanced finite element simulation to develop improved, I'll call them crush models, basically force deformation models for vessels, validation at different scales, both full scale and reduced scale. Importantly, the identification of dynamic amplification effects. I'll talk about that a bit. And then equally importantly, how do we efficiently capture those amplification effects using efficient dynamic analysis? Okay, so to get started, I'm just going to give a very brief overview of some portions of the AASHTO code. I believe later presentations will probably cover this in more detail, so I'm just going to give a brief overview here. The AASHTO risk assessment procedure involves looking at the the characteristics of both the bridge as well as the vessel traffic. We've heard about AIS data. In the state of Florida, we also have a database of vessel traffic that catalogs vessel traffic around the state. But the bridge characteristics and the vessel traffic characteristics are used to evaluate the contribution to annual frequency of collapse for a particular bridge element, for example, a pier. And I've graded out some of the things I'm not going to be talking about here in great detail, but I'll go ahead and name them. These include the number of transits of a particular type of vessel or vessel group, the probability of aberrancy, the geometric probability that an aberrant vessel would actually strike an element like a bridge pier, a protection factor, and then finally, the probability of collapse expression. The probability of collapse expression in AASHTO is sketched here. I think it's been given previously in equation form. But what I want to point out here is that the denominator of this is the demand on the pier. The numerator is the capacity or the resistance of the pier. The denominator is the demand, and very often that's taken as the force applied to the equivalent static force that's being applied to the pier. So those annual frequency of collapse contributions from each element are summed over all of the elements in the structure, and then that final value is compared to an acceptable level. So again, the probability of collapse expression in AASHTO is a function of the demand on the pier as well as its resistance or capacity. Very often the demand is taken as being equal to the equivalent static impact force. And so I'm indicating PB here, the barge impact force, but we've seen the equation previously for PS, the ship impact force as well. So the process for barge impact, at least, is that's included within AASHTO is to start with a kinetic energy calculation. We take the mass and the velocity, calculate kinetic energy. That kinetic energy is correlated to a crush depth, a vessel crush depth, and then that crush depth is correlated to an impact force, an equivalent static impact force for application to our bridge model, for example, if we're doing a structural analysis. All right, and so again, that in this case, the equivalent static force is the denominator of the C over D. That's the force applied to the structure or the demand on the structure, at least characterized as an equivalent force. All right, so the question that I want to talk about just for a moment with respect to barges is, where does this force deformation relationship come from? Can we improve it? And how can we use an improved version in dynamic analysis? So first of all, the history, just a brief history, the AASHTO crush curve or force deformation curve for barges is based on tests that were conducted in the 1980s by Meyer-Dornberg, where reduced scale barges were used to drop hammer tests were conducted on reduced scale barges. You can see the data here. The development of the AASHTO included fitting a reasonable approximation of that relationship, and then adding to that an elastic portion of the curve. So the AASHTO force deformation curve is elastic up to a transition point, and then plastic with hardening. Okay, and so you see a photograph of typical crush depth here. This is actually from our St. George Island barge impact testing, which I'll show in a moment. So we have used advanced finite element modeling, high resolution modeling using LS-DYNA for many years to investigate the effects of different characteristics on these force deformation relationships. So we've looked at different types of barges. Again, our focus for the most part has been on barges. So hopper barges, tanker barges, the effect of different pier geometry. So the shape of a column, the shape of a waterline footing, like a pile cap. Does it have a rounded face? Does it have a flat face? What are the dimensions of those elements? These all enter into or all influence the impact forces that are generated during a collision, or technically an elision. We've also looked at the effect of impact angles as well. So to summarize a few of the findings that relate to barge impacts, we found that both the shape and the size of the impacted surface of the bridge element affects the forces that are generated. So for example, we have found that rounded geometric surfaces of the bridge produce, generally speaking, smaller impact forces or result in smaller impact forces than do flat-faced impact surfaces, such as, again, a rectangular pile cap, waterline pile cap is an example. Furthermore, for the flat flat-faced impact surfaces, the dimension of that surface strongly influences the forces that are generated, eventually transmitting load into the structure that's been impacted. So to illustrate some design implications of this, just very, very briefly here, if we consider a particular collision incident where we have a fixed mass of the vessel and a fixed velocity, in that case, the kinetic energy is fixed, and so therefore the force, or the equivalent static force, is also fixed. What our research has shown here at the University of Florida, both through FEA modeling and through physical testing, is that in fact the forces are different. They vary based on shape and size. And so we can gain some design efficiency from acknowledging that and making use of that information. As an example, if we look at the effect of pure shape, two different piers with, let's say 10-foot wide impact surfaces, the rounded geometry case will produce loads that are significantly less than a flat-faced impactor. And going to a flat-faced, let's say pile cap geometry, can increase our design loads by approximately 60%. Likewise, if we move from a relatively narrow pier to a wider pier surface, once again, about a 50% increase in the impact force associated with nothing more than changing the geometry of that impact face. All right, so taking this kind of information into account can help us with designing structures more efficiently. So as I said, we used Ellis Dyna simulations for a number of years to look at lots of different scenarios. I'm showing a couple of examples of crush simulations here for barges with a relatively narrow 6-foot wide pier and a wider 35-foot wide pier, both at 5-degree angles, and you can see the corresponding crush simulations. We've done this over a wide range of angles, as you can see on the left-hand side of the slide, going from head-on 0 angle all the way up to 45-degree angle, and then very narrow pier widths of 6 feet all the way up to the full width of a jumbo hopper barge, 35 feet. So from those kinds of simulations, we extract force deformation relationships. We apply some statistics, which I do not have time to get into right now, but maybe we can talk about that later if we're interested. But we apply some statistics to this, and then we produce out of the combination of the statistics and the finite element modeling a revised force deformation relationship for vessel impact for barges specifically. So this is an elastic, perfectly plastic force deformation model. So that is a difference from what's in AASHTO. You can see the AASHTO curve on the left-hand side here, where we have elastic and then hardening. So we have a hardening modulus on the post-yield behavior. In terms of determining the plateau level on this elastic, perfectly plastic curve, we use the figure that's above, where we go into this plot with the size of the impacted surface, for example, a pile cap or a column, and then we intersect the appropriate curve. So in the case of flat-faced impactors, we make use of the angle, the deviation angle, basically between the transit path of vessels, basically the waterway alignment center line, and the face of the pier. So, for example, if we had a 25-foot wide surface and a 30-degree deviation between the waterway alignment and the pier face, that would tell us that for a barge impact, we'd have something less than 3,000 kips as our maximum value. So that then becomes the plateau level on this elastic, perfectly plastic force deformation model. These force deformation models then can be used either in equivalent static design, or what I would recommend is we use this in an efficient low-order dynamic analysis to more accurately capture dynamic phenomenon, as I'll talk about as we go forward here. So this is all based on finite element modeling, and there's always a question as to the validity of finite element modeling. And so in the state of Florida, we've invested significant effort in physical testing, both at full scale and reduced scale, to develop confidence in the results from the FEA modeling. A number of years ago, we conducted full-scale barge impact tests on the St. George Island Bridge, which is in the southeastern portion of the United States. It's actually up in the northwestern part of our state, and it connects the mainland of Florida to St. George Island. It's about a 4-mile long bridge. A number of years ago, we had the opportunity to run full-scale tests on the old bridge once the new alignment and the new bridge had been open to traffic. So we did that. We tested 2 different piers in the structure. Pier 1, which was adjacent to the navigation channel, and then Pier 3, which was third from the navigation channel in terms of positioning. We used a 600-ton barge, and we had instrumentation, a variety of different types of instrumentation on the structure, including load blocks, accelerometers, displacement transducers, and a lot of other types of sensors. We tested the bridge in 3 different configurations, 2 different positions, but 3 configurations. So we tested the channel pier in isolation. The superstructure had been removed. We tested pier 3 in what we call a bridge configuration, where the superstructure was still in place. And then we tested pier 3 again after the superstructure had been removed, because we were very interested in what the effect of that superstructure would be on not only on the generated loads, but also on the response of the structure to those loads. So I'll show one quick video here. I believe the audio will come through. So this is the last test on Pier 1 at St. George Island. And then some example or representative data sets from that testing. For some of the cases on Pier 1, we generated over 1 million pounds of impact force. For the Pier 3, which is a smaller pier, lower levels of load. What I'm showing here are traces or time histories of impact force for the case where Pier 3 was struck with the superstructure in place and without. And what I want to point out is the difference in the dynamic characteristics or the dynamic response of that structure with and without the superstructure. And that's those differences are a function of the influence of the mass of the superstructure, as I'll come back to in just a moment and talk about. Now, as a result of safety considerations at St. George Island, we were only able to generate up to about 16 inches of deformation. Our finite element models and using the finite element models for developing design recommendations obviously go to a larger deformation level. And so we had an interest in validating the barge models at higher deformation levels. And so we did this at 0.4 scale, 40% scale, by designing and constructing a gravity pendulum at the Florida Department of Transportation. So we at UF designed the facility for the DOT, and then it was constructed, it was constructed, one more time. There we go. Constructed and has been operational for a number of years at the Florida DOT. And so we ran 40% scale tests. Let me go ahead and let this run. 40% scale tests on 2 different barge specimens. We used 2 different impactors, because part of what we were trying to validate is the influence of the shape of the pier. And I will point out here that we're swinging essentially the bridge pier at a stationary barge. We've kind of turned the typical impact around. Finite element results showed that the force deformation relationships that derived from swinging the pier at the barge or the barge at the pier are virtually identical. And so it's more expedient to and more controlled to swing the pier at the barge. And so that's what we did. But we tested with a rounded faced impactor and a flat faced impactor so that we could determine whether or not the results from the finite element simulations that said there are different force levels were proven out by testing. So here are a couple of quick clips from the flat faced impactor testing. And the initial impact on the other barge. So again, we had 2 barges, each of which was struck by an individual impactor. So this is the first impact on one of the barges from the rounded impactor. So we had accelerometers, high-speed cameras, and a number of other types of instrumentation to measure and extract from these tests the force deformation relationships. So what you see here in the upper left plot are comparisons of the experimental data for flat-faced impactors versus rounded. And so the test data did confirm that flat-faced impactors generate, generally speaking, larger force levels than do rounded-faced impactors. And so again, that's information that's useful for design, at least for barge impacts, in terms of being able to reduce their design loads. We also compared our FEA data to the test data, and that's shown in the bottom left, at least for the rounded case. And so again, very reasonable comparisons here between the test data and the finite element simulation. And I'm overlaying with, on top of that, an elastic, perfectly plastic curve, which is what we recommend. So the AASHTO curve, as I pointed out earlier, does have a hardening modulus on it, so we can gain some efficiency by using an elastic, perfectly plastic curve. All right, so advanced FEA of this type, and again, these are all LS-DYNA simulations. This is a very powerful tool, and it allows us to gain very important insights into dynamic characteristics, behaviors. However, the model sizes are typically very large, over 100,000 elements, up to maybe a few million elements is very typical. Run times, even with very powerful computers, we're talking days, hours, days, possibly weeks. And so while they're very powerful tools, they're not necessarily practical for routine use in bridge design. And so what I'm suggesting is we can use the information that we obtain from these high resolution models to develop efficient nonlinear dynamic models that have run times on the order of minutes, maybe an hour, maybe an hour or two at most. So much more manageable for use in typical design practice. So that's what I want to talk about for the remainder here is a number of years ago, I developed this idea of a coupled vessel impact analysis procedure where we take all the information I've talked about so far, so physical testing, high resolution modeling, and so forth. We develop crush curves or force deformation relationships and then concentrate the mass of the vessel into a small number of degrees of freedom, in this case, a single degree of freedom. And then we represent the stiffness of the barge, or in this case, the vessel, with a nonlinear spring, okay? We then couple that to a multi-degree of freedom representation of the pier. So that can represent the stiffness characteristics of the pier, the mass characteristics, the soil conditions, and so forth. And then the analysis is performed in a dynamic mode in which we actually calculate the impact force as part of the analysis results. So we don't pre-calculate the impact load. It's calculated as a outcome of this process. And we implemented this in the FB Multi-Pier software, which is distributed by the Bridge Software Institute a number of years ago, and it's been available for some time. The question, of course, is, does it work, right? Do we trust it? How well does it compare to physical test data? And so we applied this to some of the conditions from the St. George Island testing, and that's what I'm showing here. So the upper plots are both force time histories for the case where we tested a pier by itself, and then later a pier connected to other piers through the superstructure. And we see reasonable agreement in terms of forces, but even more important is the response of the pier to those loads, all right? And so that's shown in the bottom plot. So very good agreement there. Applying the coupled vessel impact analysis to a wide variety of different bridge types, one of the things we found is that the mass distribution, or the mass of the superstructure, has a very important effect. So bridge designers very often include the effect of the superstructure stiffness as a way of shedding or sharing. You can choose your word there, sharing the load, the impact of load to adjacent piers. What we found is that the mass of that superstructure also has a very significant influence on the forces that arise. And so taking an example here, this is the B3T4 case, Bridge 3 Test 4. What you see in the upper left is the computed time history of impact force dynamically. And then we took the peak value from that and applied that as an equivalent static force to the same model, and then calculated the demands and those demands include column shear, column moments, and bearing shears. And what you see is that the dynamic demands are more than double the demands that are generated by the equivalent static loading. So a very significant difference. So of course the question is, why does that occur? And in this particular case, it occurs due to dynamic amplification that's related to inertial restraint. So before I talk about that, let me talk about the static response. The static case is shown on the left, where we include the superstructure stiffness, and we apply the load statically, and we get some relative deflections within the pier, and those relative deflections give rise to moments and shears and demands. In the dynamic case, the inertia, the mass of the superstructure, produces an increased restraint at the top of the pier, which amplifies the relative deflections within the column and amplifies your design forces, as I just showed you on the previous slide. That amplification level is very structure dependent. It depends on the weight and stiffness of the superstructure, the types of bearings that are used, the stiffness of the pier, its stiffness, foundation weight if you have a large waterline pile cap, and importantly, soil conditions as well. So capturing that accurately with empirical expressions is relatively challenging, but capturing that accurately with a relatively simple coupled vessel impact analysis is a very manageable process, even within the context of analysis tools that are used in routine design. So that's kind of the end of the head-on. The thing I want to talk about with the head-on impact conditions, the thing I want to talk about with the last few minutes here is side impact and or transverse loading and oblique impacts. So this has been mentioned before, but AASHTO includes provisions for applying 50% of the head-on impact load in a perpendicular direction. And so that's illustrated in the bottom left of this figure. If we have a vessel, in this case a barge, transiting in a direction that's parallel to one of the axes of the impacted pier, AASHTO tells us to apply 50% of that load in the normal or perpendicular direction. If the direction of vessel motion was along this waterway center line, then that head-on impact load would be applied parallel to that, and this 50% load would be applied perpendicular to that waterway center line. What I want to suggest is that another way of looking at oblique impacts, at least to supplement what's in AASHTO, is to also look at the transverse component of the velocity, apply that perpendicular or transverse component as an initial velocity on a mass, a single degree frame mass, again, just for simplicity, that is then set into motion and interacts with the pier structure through a spring. In this case, the spring represents the contact interface, or this, basically the corner crushing behavior of the vessel. In this case, the vessel is a barge. So how do we generate those spring curves? Well, once again, we turn back to advanced FEA, or a fairly high resolution FEA as opposed to low order. We do a crush simulation, a corner crush simulation, as I'm showing here. We monitor the normal deformations and the corresponding forces, and pairing those two up, we get a crush curve. We get a nonlinear crush curve. All right, so we've done this for a number of different angles, and so you can see a kind of a collection or a family of different curves shown here for angles ranging from very shallow, the 1 degree all the way up to 40 degrees. These are relatively expensive simulations, taking days on a very powerful computer, but once they're computed, they become a library of functions that we can use to very efficiently model crushing for low order coupled vessel impact analysis. And so it becomes very manageable to investigate structural demands for these oblique side-on impact conditions. So some options that we have available then are to follow the AASHTO recommendations for applying 50% of the head-on impact force in the perpendicular direction, in the transverse direction. We can supplement that with a low-order dynamic analysis where we also capture the potential amplification effects or dynamic effects within the pier by conducting an efficient lateral dynamic analysis using those crush curves that I just mentioned, and then corresponding components of normal velocity, initial velocity. All right, so to summarize, my recommendations are to use improved force deformation models for barges and ships. So we've talked about how we've done this for barges. I know some of the other presentations have talked about this similarly for ships. And then to use those simplified representations in some sort of a dynamic analysis. So that can be an LS Dyna simulation, which is warranted for some cases, or a simplified analysis technique like the coupled vessel impact analysis procedure. Static versus dynamic, the static procedure does not generally, or at least does not rationally calculate or capture dynamic amplification effects. Again, we can try to empirically capture that, but it's fairly challenging to do so. And as a result of that, the static approach tends to produce a wider range of variability between what we expect to be the vulnerability of a bridge and what the actual vulnerability is if we look at it dynamically. So there's a much greater spread in terms of the risk level across a large number of bridges, and that's as a result of the differing dynamic characteristics of bridges. So dynamic approaches that are available to us, again, LS Dyna, very high resolution analyses are certainly very useful and would be appropriate for some cases, but not all cases of bridge design. A more simplified, efficient procedure like the coupled vessel impact analysis procedures or methods of that type are simple enough and efficient enough to be used in practical design by bridge designers. And so that's another option. Finally, in terms of pier protection, obviously dynamic approaches are quite appropriate for designing energy dissipation systems that protect either completely or partially bridge piers from impact by either arresting a vessel or reducing its kinetic energy. So with that, thank you for your attention. I want to acknowledge the Florida Department of Transportation for research funding and experimental support, testing support, and also the U.S. Army Corps of Engineers for research funding that contributed to this presentation. So thank you very much.
Right, Gary, thank you. We have just a couple of minutes for questions. So one of the questions here from an anonymous attendee, he had asked this question, or she, before, and the question is, the question on the need for substructure characterization and lab testing, not PY curves, as was cited by the presenter. That person found that the answer was not satisfactory. So what do you think? I mean, how would you get the response of the substructure, and how would you model that?
I'm not sure what you said the question was, but was it that they felt that PY curves were not appropriate, or
yes, they felt that the need for subsurface characterization, like how, I guess maybe I would rephrase the question. How would you get an accurate PY curve, maybe?
So PY curves, so we have several tools and a number of different models for modeling different types of soil with different at different depths. And so the PY, the approach we generally use is the PY approach. It's a Winkler spring model where we use distributed springs to represent the effect of the soil. And that is generally found to be adequate. When we did the St. George Island testing, we did look at different ways of also including mass contributions from the soil surrounding the piers. And but there was some influence on the stiffness of the soil as a result of the dynamic resistance of the soil. But within the kind of greater context of other uncertainties in terms of impact conditions and so forth, we concluded that using a PY approach is generally adequate.
There was a quick question here. Have you tested this from John Horvath? Have you tested a pointed or knife-edged pier shape? I didn't see that in your presentation, though.
We have tested relatively sharp angled shapes, and they with vessels such as barges, they tend to split. I think I showed one photo there actually of a I don't want to spend too much time here, but if I can jump back to it quickly. There we go. I think I just went past it. So this was on the bottom left of this figure. This is an actual impact incident that occurred, and we simulated this with a sharp cornered impactor and saw that we saw fairly similar responses in terms of the vessel. So I'm not sure if that's a question. Is it a sharp-faced impact surface as a way of kind of splitting the structure open?
Yes, I believe that is the implication. I got another question here. I'm not looking for an answer, but this seems to be of interest to the audience regarding the PY curves. So it's saying for how would regular PY curves for lateral loading be suitable? I'm not asking you to answer it, but I'm just making a point that people seem to be very interested in that.
So there's a fair amount of literature and tools available for calculating PY curves for a number of different types of soils, group effects in pile foundations and drill shaft foundations and so forth. So there's a lot of guidance out there for that.
Sounds good. Gary, there is a question from Nitesh Sangam. Can we use FB multi-pier to perform the coupled vessel impact analysis?
Yes. Yeah. Coupled vessel impact analysis.
Okay. And one last question from an anonymous attendee is that you're showing the force time history curves as spanning maybe 0.2 to 0.3 seconds. That is similar to truck impact situations, but in heavier loaded vessels where the impact depth is longer, the process is much slower, and therefore the dynamic effects may not be as severe. Can you comment on that?
Sure. Yeah, that is a possibility. The durations I'm showing here. So as I said, the masses you're seeing here relative to the large ships that we've seen in the other presentations are obviously much smaller. The bridge structures that we're applying these impact conditions to are also smaller. And so the question would be a longer duration impact event with a more massive vessel. You're also striking a much larger structure. And so ultimately it comes down to looking at the dynamic characteristics of that structure relative to the time duration of the load that's being applied. And so, yeah, it's not a one size fits all. And that's actually part of the reason that I'm making the argument that a method like the coupled vessel impact analysis procedure makes sense, because you don't have to fit the potential for amplification effects into an empirical model. If dynamic amplification is an issue, it naturally arises out of that calculation. If it's not an issue because the natural period of the structure and the duration of the loads, as you just pointed out, are significantly different, then you won't see significant dynamic amplification that naturally comes out of that process.
Okay. Gary, thank you very much. And Anil, back to you.
All right, thank you.
Thank you, Gary, very much for the presentation. And we move to the next one. We have Scott. Can we? Yes. So our next presentation is on the risk analysis of ship collisions with bridges by Mikele Scott and Mike Winters. Mike is Vice President Emeritus of Moffat and Nichol, and he has been he has done a lot of work in this area. He has been the principal author of the ASTO Guide Specs on vessel collision design highway bridges. He has extensive expertise on ships and barge collisions with bridges and marine structures. And he's the author of numerical technical papers and publications related to vessel impact. And on standby with him is Mike Winters. Scott, can you go to the next slide? Mike is principal U.S. rep to an international committee established by the Permanent International Association of Navigation Congresses to develop guidelines associated with ship and barge collision with bridges and other fixed structure. His interest is the vessel collision risk analysis, pier protection design for numerous bridges and other waterfront structures. Presentation will be made by Mike, but I think Mike Winters also is going to be on standby if we have any question. So Mike, it's all yours. I'm inviting you to make this presentation.
Okay, thank you. So I'll be doing the speaking. Mike Winters is going to participate in the panel discussion later on. So accidents do happen. I've often said if you build it, it will be hit. That's true of almost any waterfront structure, whether it's a pier or a terminal or something in the water. It's only a matter of time, which is an element of risk. And there are consequences to bridge collapses. People die, oil spills occur. There's political turmoil, people get fired, major transportation disruptions, large economic losses. About half of the major collapses since 1960 have occurred in the US. And just to note that on average, there's about 5 minor collisions a week in the US, mainly on our inland waterway systems that don't do serious damage, but yet it just shows that things in the water will be hit. So collapses occur everywhere. On the inland waterway system due to barges, on our coastal waterway systems due to larger ships. Collapses occur for highway bridges. They also occur for railroad bridges. 1980 was a turning point. The Sunshine Skyway Bridge in Tampa was hit. 35 people were killed. The lower left shows a picture of the accident. I'd like you to be aware that the vessel did not hit the main pier. It hit the approach pier. Twice as many bridges collapsed due to ships and barges hitting approach piers than they do the main pier adjacent to the channel. The upper right shows the bow of the Summit Venture, a minor crease in the hull. That ship came in, took on a load of phosphate cargo, and took off 2 weeks later. Also in 1980 in Sweden, the Tjorn Bridge across Alma Sound in Sweden collapsed. The lower right is a photograph of the bridge as it was built. It was received a number of international architectural awards for beauty. And yet we learned a valuable lesson. Don't build arch bridges over navigation channels. At nighttime, a vessel that was slightly off course, the deck house of the ship contacted the arch and the bridge collapsed. In 1988, there was a pooled fund research project sponsored by 11 states and the Federal Highway Administration I had the privilege of being the leader of that effort. Included on that old research project were Ole Damgaard Larsen from Denmark, naval architect Gerhard Weissing from Germany, and input from Dr. Fuji in Japan. Those investigations led to the 1991 AASHTO guide specification, which for the first time provided information to designers on how to consider vessel collision as part of the design process. Somewhat recently, the guide specification has been superseded by the AASHTO Bridge Design Code itself. And I just highlight the guide specification had over 200 pages of great vessel information about the equations and where they come from and how they were developed. It has some worked examples in it. That's been reduced to 20 pages in the Bridge Design Code. And so if you're involved in vessel collision design, you really should have a copy of the guide specification. It's a critical reference. Strangely, it's not in the AASHTO catalog, but it can be searched for and found on the AASHTO website and downloaded. So the risk analysis process is basically used to estimate the risk of bridge collapse. And that estimate of bridge collapse is distributed amongst the various bridge piers in the waterway. And from that, we can determine a design vessel for each bridge pier. It's not one design vessel for all the bridge piers. Each pier could have a different design vessel. There could be a different design vessel for inbound versus outbound traffic. The code includes very basic, very simple examples of things to consider. And so these very simplified concepts need to be used by engineers to evaluate more real-world situations. We do have curved navigation channels. We do have side channels coming in near bridges. We have modern electronic navigation systems, and the ship and barge bow crushing behavior is something that an engineer should consider. I won't go through all this. I understand that copies of these presentations are available to participants, so you can go through the details. There's basically a process where we get information about the waterway, channel geometry, water depths, currents. We get information about the fleet passing under the bridge, the vessel types, its loading conditions, its transit speeds, the vessel transit path, and the number of vessels passing in any given year. Of course, we get information about the bridge, its type, size, location, the spans. Important is ultimate impact resistance and geotechnical data, as well as scour information. This is taken through an analysis process that results in an estimate of the probability of collapse and also the selection of a design vessel. Well, if it doesn't meet the criteria, then something has to change. Either add pier protection to protect the bridge. If it's a new bridge, make the spans longer. You continue through the analysis until you arrive at a solution that's acceptable. Vessel characteristics, of course, is extremely important. The type of ships, this just illustrates containers and cruise ships and bulk carriers and tankers. These are ship type vessels. This presentation is not considering barge vessels directly because the topic is more on the large ships. Articulated tug barges are essentially ship hulls being pushed by a tugboat. So fleet characteristics is critical in doing the analysis. The AASHTO guide specification is over 33 years old, and so vessel types have changed quite a bit since then on the larger end particularly. The upper right is a recent PANC publication on ship dimensions and data design for marine infrastructure. This is a good resource now for vessel types and shapes, and is what we use when we do our analysis. I wanted to highlight here, though, that ballasted vessels are critical in the analysis. The lower left shows a bulk carrier that's empty, and I've even seen ship bows where the bow is sticking up out of the water. So it's very important to include the ballasted or empty condition when doing your risk analysis. And so your your ship might be 45 feet deep loaded and you have a pier and 30 feet of water, and maybe that vessel runs aground. But in the ballasted condition, that vessel might only have 9 feet of water at the bow. It's 1,000 feet long. It can potentially strike your pier, and you should be considering that. AIS is an important modern tool that's been talked about earlier. Downloading AIS for a particular calendar year will give you the names of all the vessels that transited the waterway. We can plot their paths as shown in the black in the upper part of this slide. We can even plot individual vessels as shown in the red and green in the bottom, and at 5-second intervals where that vessel is located, and particularly when it's passing under a bridge. This does require some specialized post-processing software, however. These days, we often consider as part of a protection system non-physical things that affect the vessel operation and maybe navigation in the channel. A good tool for evaluating that are ship simulators that we actually can put a pilot in the loop and run through some simulations to test out various alternatives. Design impact speed is critical. It's probably one of the major factors in estimating the impact force. And also the impact energy. The energy, of course, goes up by the square of the velocity. The faster it goes, the more energy. And the vessel isn't stopped until the energy is absorbed. So it's not enough just to put a force on a bridge pier, because the energy associated with that force may require a movement of 10 feet, 20 feet. And can your bridge sustain that? Probably not. So the ideal situation is a long main span over a narrow channel. The problem situation is a small main span over a wide channel where the bridge piers are located close to the ship and barge movements. This is the code allows the impact speed to be reduced as you move out of the channel. Within the channel, the vessel is allowed to go as fast as it's allowed. But outside the channel, the impact speed is reduced. So the further away the pier can be, the less impact force you need to consider. I'll highlight here that these distributions are based on the vessel transit path, not the center line of the channel. So if the vessel is two-way traffic and it's sticking to its side of the channel, then the distribution moves to the right-hand side of the channel for inbound traffic, and it'll move to the opposite side of the channel for outbound traffic. And so they are different. The annual frequency collapse is based upon a number of factors. It includes the number of vessels passing under the bridge, a factor for how often does the vessel go off course, a factor for if it goes off course, does it hit the bridge? If it hits the bridge, will the bridge collapse? Because oftentimes there are a lot of minor impacts that do not result in bridge collapse. Are there things upstream and downstream of the bridge, land masses or structures that can protect the bridge? And also a growth factor. We are looking at the lifetime of the bridge. If it's a new bridge, 100, 150 years, even an existing bridge may have a 50, 100-year remaining lifetime. So we project this marine traffic to the midlife of the bridge. I've highlighted in the red at the bottom, I guess one of my pet peeves. Every one of these factors has an engineering judgment associated with it, though they have sub-equations. At the end of the day, the engineer needs to make a reasonable, common sense decision on certain things that go into the analysis. And this is a basis of design concern to me for state DOTs and federal highway for major bridge design build projects. In a design build situation with competing firms all wanting the least cost project, it's a race to the bottom. What I'll call creative analysis is used to make the least conservative assumption of every portion of the judgment factors that go into these equations, and that the code itself can be gamed to get a result that may not be in the public interest. So how do we do these AF computations? We typically use an Excel spreadsheet. Some folks use MathCAD to automate the process. For each element of the bridge that can be hit, for example, a pier, we have a tab for inbound vessels and a tab for outbound vessels. And for each of these tabs, we have the vessel types, and then we estimate these factors that go for each of the vessel classifications, come up with an annual frequency, sum it up, then we do that for each bridge pier. This analysis also can be done for a bridge superstructure. It becomes much more complicated. The number of tabs in the spreadsheet can go from hundreds to thousands, but the process remains the same. This is just an example of a typical spreadsheet where this is an input for vessel characteristics. On one side shows the vessels. So we usually organize them from largest vessel to smallest vessel. So here we have a 120,000 DWT tanker, followed by 110, 105, 85,000 bulk carrier, so forth. So this all comes out of for us, the AIS information. The number of transit paths is also important. So for each of these vessels, we then look at inbound and outbound. Are they inbound loaded or are they inbound ballasted? Are they outbound loaded or are they outbound ballasted? And we total them up. We apply a growth factor to project the number of trips to the midpoint of the remaining life of the bridge. So once you've developed this risk model, it can be used in all kinds of ways. You can look, if you know the resistance strength of your bridge, you can evaluate your annual frequency of collapse. If you are designing a new bridge, you can put piers in different locations and determine what your strength of that bridge pier would need to be to meet the code criteria. So you can lend itself to a lot of what if type questions. So some observations on some of these factors in determining the growth over the lifetime of the bridge. We typically will go back 10, 20, 30 years in a port facility's waterway and look at the historical trend and use that historical trend to project into the future. Available water depth, we typically do the analysis from mean high water to the mud line. But if your mud line is full of very soft, silty soils, vessels can plow right through that as if it's nothing there. And so understanding that and allowing for this plowing effect of vessels through soft soils is important in doing a risk analysis. The probability of aberrancy is how often will a vessel go off course. It's based upon some empirical equations. What I wanted to highlight here is that we break the vessel transit path into a series of straight tangents, and that the probability of aberrancy is applied to these tangents. The piece of A in the code should be applied on both sides of the bridge. It's not one piece of A where you take half for inbound, half for outbound. The full value of piece of A should be on the inbound track. If you have 5 segments of your inbound track, 1/5 of that can be applied to each of those segments. So then there's a relationship here for probability of aberrancy. There's a base rate for collisions, different one for ships than for barges. There's a correction factor for if your bridge is located near a turn, how steep that turn is. There's a correction factor for currents acting parallel to the vessel transit path, correction factor for cross currents that want to push the vessel sideways, and a correction factor for vessel traffic density. I just want to say this is a highly simplified equation that, of course, there's many more factors that go into a probability of aberrancy. I've seen equations with 10 factors, 20 factors. You could develop a very elaborate fault tree type analysis with 50 factors in it. Each of those sub-factors, though, have to have your own estimate of the probability. And at the end of the day, a lot of those are educated guesses. And so you have a very elaborate model of educated guesses that is very sophisticated. But then at the end of the day, is the result that much different than a more simplified model? This equation basically seems to work. Can it be improved? Maybe, but it does seem to work based on historical bridge collapses. Well, the code base rate's based on one pilot, no other navigation restrictions, no tug assistance, but these days We have harbors where multiple pilots are required, tug assistance is required, daytime restrictions sometimes, current restrictions, speed restrictions. Sometimes there's a vessel traffic surface. Portable electronic navigation devices is used by all pilots these days. A lot of these things were not considered when the guide specification and the subsequent code was developed. And so adjustments for these things can be made as part of modern bridge analysis. Geometric probability is if the vessel is out of control, where might it hit? This is also an empirical equation based upon real-world accident rates. To say again that the center of this normal distribution is not the center line of the channel, it's the center line of the vessel transit path. So if there's two-way traffic, this is moved to the right side of the channel for inbound traffic and the opposite side for outbound traffic. The geometric probability is if the vessel is aberrant and out of control, where might it hit? And this is not, in my opinion, this is not something you get from AIS. AIS shows where the vessels are that are behaving properly and navigating through the navigation channel. 10,000 transits through a bridge, it shows where they went. The 1 in 50,000 where the rogue ship has gone aberrant, that vessel could be as far as 3 times LOA, times from the navigation channel, or 2 times LOA. So while AIS data is very informational and an important resource, in my opinion, it does not tell you where the rogue aberrant ship goes. And the AASHTO code and its 3 LOA feature is to say, where does the rogue ship, where might it be located? Factors like tug assistance, this is an equation we've developed in-house that we use to look at if there is, and this applies to tethered tugs, by the way, not to tugs that are running freely with the ship. But if there are tethered tugs to the ship, the effect of this particular modification pushes the normal distribution to a very narrow value that greatly reduces the potential for bridge pier impacts. Probability of collapse is based upon a ratio of bridge resistance strength to vessel impact strength. This was developed from work from Dr. Fuji in Japan, and this curve on the right is basically based on thousands of collisions of small ships hitting big ships and big ships hitting big ships and big ships hitting small ships. And so it was the best approximation we had in developing the code on what a probability of collapse function might look like. The ship impact force is a very simple equation based upon speed and deadweight tonnage. Again, this is a highly complex, one could put all kinds of equations with all kinds of sophistication to it, but this was a relationship that seems to work. So a 100,000 ton ship moving at 10 knots has an impact force of about 43,500 kips. The upper right was some relationships developed by naval architect Gerhard Weiss-Sinn, where impact force over time of a bow hitting a rigid wall over a 4 or 5 second period of time, for 1/10 of a second, there's a maximum impact force, and then it quickly goes into this average impact force that lasts the remaining part of the impact. So the question was, well, which force do you apply to the bridge pier? Is it this maximum impact force for 1/10 of a second, or this long average impact force over 4 seconds? And in AASHTO, the judgment was we would use this long-term average as the force to the bridge pier, not the maximum impact force. The lower right is a graphic from the guide specification comparing researchers and their suggestions on impact forces. And I'll leave it to you to look that up to understand some of the differences. Protection factor, if it's a narrow waterway, say for barge traffic, barges aren't going to come at your bridge pier from a lateral direction. They'd be running aground on the riverbanks. So the protection factor accounts for waterways, the riverbanks, upstream obstacles. This is also where we model our pier protection alternatives, if it's an island or a dolphin or a pier protection structure. Again, we use a normal distribution as a best estimate of what that might look like. When vessels are in trouble, oftentimes, if they're not moving straight, they're moving in a turn associated with the rudder at a maximum angle. This runs to be about 3.5 times the diameter, a diameter 3.5 times the LOA of the vessel. And so we oftentimes will take a vessel in a waterway and using this as a vessel path, look at the different angles a ship or a barge might hit a bridge pier. And so the yellow segments in the graphic on the right are where the pier is exposed to collision and where you would consider putting pier protection devices to protect it. On this particular example to the right, it's a highway bridge next to a railroad bridge. The railroad bridge protects the highway bridge from ship impact. Of course, the railroad bridge will be taken out, but the highway bridge would be protected. But that also can be modeled in the risk analysis. I talked about how we break curves into tangents. So here's a vessel transit path that is on a tight curve. We've broken it into a series of tangents. Each of those tangents has its own risk analysis. So you have to add up all the tangents to get the particular bridge pier. But this is how it's done. Another example of a bridge, on the inbound side on the left, you can see a series of straight segments. And so this is breaking the vessel transit path into some tangents. Each of those tangents has its own vessel, its own normal distribution and how it might impact a bridge pier. The outbound vessels in this example are on a straight. And this is also an example of two-way traffic where the normal distribution is on the center line of the vessel, not on the center line of the bridge. Impact forces and their location. This is critical. Probably the code could do better at highlighting this. This is how the Sunshine Skyway Bridge collapsed. It was the flare of the bow way above water that caused the collapse of the bridge superstructure before the bow of the ship contacted the foundation underwater. This is probably going to be the same situation for the Key Bridge in Baltimore. The flare of the bow, which you can see in the upper right, contacted the weaker bridge pier, causing the superstructure to collapse. And then there may have been an impact of the portion of the ship bow underwater made contact, but it was after the column had failed. To the bottom and lower right is an example of a cruise ship on a bridge pier, and the fact that, again, the overhang of the bow is something that must be considered when developing protection alternatives for existing bridges. These days, we can use some fairly advanced models. We use explicit solver finite element modeling. Just to show a little animation here. This is a small bulk carrier impacting a suspension bridge. And as was mentioned in a previous speaker, we actually found a little bit of bounce back from the ship hitting the bridge pier. We use similar modeling to look at protection systems. So to the left here is a large diameter dolphin being impacted by a vessel, and we're looking at the deformation of that dolphin, its ability to absorb the ship energy before the ship makes contact with a bridge pier. And we also use similar models to look at the grounding of ships and the plowing of ships through soft soils. So typical pier protection alternatives for bridges controlled by ship collision, dolphin structures, pile supported structures, protection islands are usually the typical alternatives. For bridges controlled by barge collision, sometimes the piers can be designed for the impact forces. Sometimes a fender system, which can be either elastic or sacrificial, can be added. And sometimes dolphin structures are placed near bridges subject to barge collision. I will say Mike Winters and I are presenting a presentation next Wednesday before the IBT ABC monthly seminar. And our topic will be focusing on pier protection structures and ship impacts and ship energy, if you're interested in that next week. So final thoughts, things that I think you should know as a bridge design community. Bridges are obstructions to marine navigation. Mariners have the right of way, not motorists on our waterways. Bridges must provide for the reasonable needs of navigation, and bridges are permitted to be built as obstructions to navigation by the U.S. Coast Guard in the United States, where we get the name bridge permits. Bridges must be maintained in accordance with U.S. Coast Guard permits. Woe to the state DOT that is not maintaining the bridge according to their Coast Guard permit. If it is hit, when you go to Admiralty Court, and these collisions are handled in a special court called Admiralty Courts, you might be held responsible for the accident rather than the vessel that hit it. Last point, vessel collision vulnerability studies in the US are highly confidential. They are classified, and if disclosed, those who disclose that are subject to criminal penalties, possibly loss of professional engineering licenses. And so studies have been done on bridges in US waterways, looking at vulnerabilities, particularly after the terrorist attack of 9/11. These are not public documents. They cannot be disclosed. And engineers need to be careful in their discussions. Thank you. That's a summary of the things I wanted to say, and I'll be glad to entertain any questions you might have.
Michael, thank you very much. We have a number of questions that are online. So the first question is, it's probably a quick question to answer, is that can each state Department of Transportation decide on its own whether to use the AASHTO document for existing bridges, or are these rules establishing when must be used for existing? Like, can individual departments of transportation determine to use their own guidelines, or must they follow AASHTO? That's the question.
Oh, it's a good question, and I'm not sure I have the absolutely correct answer, but my understanding is that yes, within a state DOT can establish standards for bridges in their state. So Florida, for example, has some standards for barge collision that supplement the AASHTO code, might be in addition to the code. And so states do have the ability to make those decisions.
Okay. How about malicious impact? Would the risk computations mask this possibility? You mentioned towards the end that investigations related to ship bridge impact are confidential, but right now the design provisions are all, you take the risk of this and risk of that and multiply them all together. It seems to mask a lot of what's happening. How about malicious impact? How is that handled?
Well, we're talking about terrorist attacks here.
Yes.
Where a vessel could be pirated and intentionally run into a bridge pier. That is a scenario that has been, for most states, looked at. Again, these are highly confidential. I cannot get into details other than to say that impact, speed, and energy are based on impact, force, and energy are based on speed. And so you take a vessel that's transiting a waterway at 10 knots, and then you have a hijacked vessel that is going to be going maybe 16, 18 knots. The forces and energies go up accordingly. And so it becomes something that those who own infrastructure consider and is part of their evaluation system of what they do.
From an anonymous attendee, we have seen that AASHTO significantly underestimates impact force. Where do we go in terms of code to address it?
Well, I would disagree that it significantly underestimates. I think for the most part, the forces that AASHTO predicts are pretty much in line with studies that have been done. I think from this morning's discussion, some of the really larger vessels maybe have higher forces. Those larger vessels don't apply everywhere in every waterway. Most of those are really big vessels. in fact, can't even enter US waterways because their drafts are too deep. And so certainly if there's research and data that supports increasing the loads for some of the larger ships, that should be looked at. And so I think in terms of an industry standard, new bridges designed to the code are reasonably safe. If we learn better and we need to make adjustments to the code, that's something that we should do. But I would say that we're reasonably close, but that if there's some adjustments to be made for really large vessels, that's something the AASHTO Bridge Committee can consider.
Okay. Michael, thank you very much. There are a number of other questions, but these will be shunted over to the discussion panel. I appreciate it. Anil, back to you.
Thank you, Mikele. Again, very, very insightful and, detailed presentation. And we learn a lot about what is the state of the art. So we move on to our last presentation before our panel discussion. We have David Taylor right now from New Zealand, and I think David just woke up. It's 6 in the morning, or slightly after 6 in the morning there. So thank you, David, for waking up, and sorry to wake you up. David has expertise in managing technically complex projects across a range of engineering and applied science disciplines, site selection for coastal and port infrastructure, and design of coastal structures, risk and hazard assessment, and coastal and navigation risk assessment. So with that, I will invite David for the presentation. Scott, can we start his presentation and pass him the mouse, the control? Good, thank you.
Thank you very much, and thanks for this opportunity to give a presentation on my experience and expertise in this area. So with my presentation, I'm going to be giving an example of a large-scale risk assessment and mitigation. It's not specifically focused on bridge impacts, but it's focused on, I guess, the same drivers around major navigation incidents that lead to blockage and of critical infrastructure. And so in this case, it's a severe vessel grounding that leads to blockage of a major economic output pathway for the Australian economy. So it's based on one of our major export ports in the remote northwest of Australia. And then, but the framework and approach to looking at risk assessment, I'll provide an example of a similar case study in Australia that's actually specific for a bridge situation. So just to provide some context of the site that I'm going to be talking about today. So Port Hedland is located in northwest of Australia. On a world scale, it's one of the largest port operations. It is the world's largest bulk export port, and through a single channel, exports approximately 560 million tonnes of iron ore each year. It has an annual economic benefit of about $60 billion US in trade each year, and it has around about just over 3,300 ship visits per year. And the majority of those ships nearly all of them are Cape-size bulk carriers and very large ore carriers. So generally 175,000 deadweight tonne up to 275,000 deadweight tonne. Now, when ships visit Port Hedland, so it's quite a unique environment. It's a 7.5 metre tide range, and the port operates using that tide assistance. So vessels come into the port in the low tide situation when they're ballasted. They fully load to around about 18 to 18.5 metres draft, and then all of the ships depart the port using the assistance of the high water in that 7.5 metre tide range. And then they need to transit a 22 nautical mile channel, which is shown here on the right, and until they're in open water. And the first 10 nautical miles of that channel is a confined channel where, at the risk of grounding, if a ship grounds, there is a risk that it can block the channel for all navigation movements after that. So the port itself has undergone phenomenal growth over the last 20 years. If we go back to the early 2000s, it was a relatively small port, exporting around about 60 to 80 million tonnes of iron ore per year. And then over the last 15 years, it's tripled in size from 180 million tonnes up to 560. And in that time, obviously the number of ship movements each year has grown in a similar proportion, and the risk of grounding has increased proportionally to that increase in number of ship movements. And so I've worked at this site for the last 20 years, and really since the sort of 2012 period of time, it's been a major effort and exercise to understand what the risk actually is of a vessel grounding, define what the consequences are, and then go through a number of exercises to work out what is the most cost-effective and technically effective options to mitigate the risk of grounding and preventing channel blockage. So apologies, I'm just trying to go back up here.
What happened, David?
Yeah, I'm just trying to go back a slide, but it's not letting me.
Scott, can you help him?
Yeah, if that's possible. Yeah, sorry. So in terms of the type of incidents that can lead to channel blockage, with that number of ship movements in the channel per year, a lot of marine incidents occur. If we firstly look at what are the root mechanical causes of incidents that can lead to channel blockage, there are two ones that we're focused on, which is engine failures or incidents to do with loss of engine control systems. And then the second one is related to steering incidents. Now, I'll purposefully define them as steering incidents rather than steering failures, because the likelihood of a steering failure is relatively low. So a steering failure being a failure of a mechanical or electrical type system in the steering systems on board a ship, whereas a steering incident is probably more likely to be some combination of maybe a relatively minor fault on a ship, and then human factors come in to the process, which actually drive the incident for a ship to then lose control or lose its navigation path, its intended navigation path through the channel. So engine incidents occur very commonly. They numerous times per year or even per month. Ships experience engine incidents when they're departing the port. It's a particularly harsh environment for a ship to be departing due to the engine load that's required to transit the channel and the restricted water depth that's available. So it puts a heavy load on the mechanical systems. related to the engines. Steering incidents are far less common, but major incidents occur on a frequency of about every 1 to 2 years. And so we now have a catalogue of about 20 years of actual data from the port, where we are able to define the frequency of steering-related incidents, including for specific areas of the transit or within the channel. So the potential drivers for a channel blockage incident occur relatively regularly, but obviously not all of them result in a vessel grounding. So really over the last sort of 18 years, there's been 3 major vessel grounding incidents. None of them have closed the port for very long. They've been able to refloat the vessel, but these provide, I guess, actual examples of what could be the incidents that could then lead to a channel blockage event. So some of the examples here, they've all got their own unique drivers. In 2008, there was a major ship grounding at the entrance, which this was actually a steering failure. It's the only really notable steering failure incident to have occurred at the port that resulted in grounding. Last year, there was a steering, in 2022, there was a steering incident that led to a very hard contact with and collision between the ship and the margin of the channel. They were able to refloat the ship quickly and get it out to deep water, but the ship sustained substantial damage to the hull. And then another example was in 2006 that a ship got pulled off its mooring and then drifted free whilst the tide was falling and actually grounded in the channel when the tide had got below a depth, a height which allowed the ship to actually float and remain grounded for the rest of the tide cycle. So these are some of the incidents that could then escalate to lead to channel blockage. Now, in terms of assessing risk, one of the unique features of the risk assessment process that we've done at Port Hedland is the use of navigation simulations. So over the last 12 years, we've completed full mission navigation simulations at facilities all around the world, where we look at different characteristics of vessel speed, types of processes and situations that occur on the bridge of a ship that may lead to a ship going off course, and then be able to actually assess mitigation, the effectiveness of mitigation options, and in particular escort towage. So just to give some sort of context, the channel is very narrow. It's approximately 180 meters width. And so these are 330 meter LOA vessels. So the time at which a ship goes off course to a ship grounding is somewhere between the order of 60 to 120 seconds. So you've got 1 to 2 minutes where a ship can be on its intended track, and then 60 seconds later, it can be hard grounded on the edge of the channel. So as a result of the navigation simulations, we have a database of now over 500 navigation simulations with where we have a whole range of different controls and different types of incident scenarios where we can actually evaluate human factors as well as the effectiveness of different mitigation options. One of the unique things that we have utilised is in 2013, we completed a 1 to 100 physical model study where we looked at actually grounding a 250,000 tonne large oil carrier in different sections of the navigation channel, and then to work out what the impacts of that were on the ship, as well as look at their particular physical characteristics of that grounding. So the things that were sort of particularly influential in that study was what the slope of the channel batter looked like. Obviously, it's been mentioned in the previous presentation, the speed of the vessel and the angle of impact at the margin of the channel. And then a particularly important factor with the large tide range at the site was what water level and tide did the grounding occur. So some of the unique outcomes from this study included that the highest risk sections of the channel were not where the channel was really heavily confined and had very steep and high channel batter banks, but were actually in the outer part of the channel where the ship would actually ground with on a section of the seabed where the channel slope, where the seabed slopes were a lot flatter, and so the contact area between the ship and the seabed was substantially higher. That was sort of the critical area for refloating the vessel. And then secondly, if a ship is to ground early in the tide cycle when the tide is still rising, most of the reaction force can actually be overcome with the rising tide, and the ship can be relatively easy to refloat within a few hours when the water level is higher. But the key risk area is if a ship is transiting near high water, that ship can remain grounded for many hours or even days to weeks, depending on which part of the tide cycle. You know, if it's falling into a neat tide cycle, it may be, you know, it may be up to 20 to 28 days later that a similar tide level might be achieved to the tide level at the time the vessel grounded. So from this study, we're actually able to develop an empirical model that, based on the transit speed and the angle of collision for different sections of the channel, we could estimate what the negative displacement of the vessel was. So what, you know, basically the negative draft that occurred at the bow, and what the ground reaction force that would be required to refloat the vessel. Now, a few years after the physical model study, we then went and looked in a bit more detail at the actual consequences and impact on the ship hull of remaining grounded on that channel margin. So I've got that example there again of the ship that grounded in 2008, where so the bow of the vessel had a negative draft of about 2 meters. So the bow was about 2 meters higher than its static draft. And then the stern of the ship was sitting within the channel. Now, fortunately, throughout the 12 hours that the ship was grounded, the stern of the vessel never came in contact with the seabed, so it was always pivoting around the bow of the vessel. Now, with these very large vessels, if you get the situation where the bow and the stern are both in hard contact with the seabed, you end up with a bending moment through the vessel, and that's you know, not a load condition that the structure can tolerate really at all. And so the critical escalation of a scenario from where you go from a grounded vessel to a vessel that is broken apart is when you get that situation where the stern comes in contact with the seabed in the channel as the tide falls, and then it almost leads to 100% likelihood of the hull failure and the ship actually breaking in half. So another example, or another incident that I've been involved with over the last 8 years is this MV Smart ship which grounded in South Africa, and that shows the consequences there of this type of failure of the vessel, where initially it was harder ground at the bow on a rock outcrop on the margin of the channel. It's a bit different to the Port Hedland situation in terms of the conditions that led to the ship grounding, but it's the same mechanism where once the stern was in contact with the seabed as well, the ship broke apart very quickly within a few hours, within sort of 12 hours of grounding. This escalation of a vessel going from a grounded situation to having a hull failure is particularly important because this is the driver for the channel potentially being blocked for a period of 6 to 12 months. And then once we had, I guess, worked through particularly a lot of those navigation simulation exercises and evaluated what were effective mitigations, whether that be from towage or bridge resource management. So how ships were being piloted and navigated through the channel. One of the key things that we've done is we've validated on water what risk mitigation can actually be achieved using those measures. So we can't do that in the confined channel, but what we've been able to do in as similar water depths as we can, but in open and unrestricted water, is that we've completed sort of fully instrumented analysis and measurement of ships and tugs in combination to work out, can we keep a ship within the channel if it experiences, for example, a severe rudder failure or a severe steering incident? Can we actually steer the ship effectively just using tugs? And then obviously steer the ship and slow it down. And the on-water trials are particularly valuable because they've highlighted a number of limitations, whether they be human factors related to bridge resource management or some of the technical limitations of vessels to be able to accommodate the power of escort towage that has been proposed or actually implemented. So here are some examples of the tug fleet, which I'll describe in a moment, that's been implemented at Port Hedland, being used to steer these large ships. And one of the key things that we had to overcome and specially implement for Port Hedland was to increase the strength of the towage bits on all the Cape-sized vessels that visit the port, so that they can accommodate the very large forces that these escort tugs are able to generate. So in terms of quantifying risk, what we've utilised is a quantitative risk assessment process. It can be described as a bottom-up risk model, and it's been developed in accordance to the ISO 31000 framework. So there's a lot of similarities with sort of the AASHTO process and formulation that Michael presented in the previous presentation. But obviously this is a particularly bespoke model, customised to the processes and factors that contribute to, in this case, vessel grounding and then ultimately hull failure at Port Hedland. But it can be broken down into really 5 key components. So the first of those is defining what the vessel transit characteristics and the environmental conditions are all the way through the channel. So each section of the channel across the whole 22 nautical miles is actually defined for vessel transit characteristics. And from that, we use a combination of using all of the available AIS data, which is thousands of vessel tracks over the last 15 years, as well as understanding for particular near-miss incidents, those outlying type events, what the vessel transit characteristics were. Then we have the second component where we actually look at, if you like, what is an instigating factor, not necessarily, I won't call it the root cause, but that sort of mechanical or failure on board the ship that may trigger a series of actions that may lead to grounding. So in this case, looking at what's the likelihood of a engine or steering related incident on board a ship, and then what's the likelihood at a particular location in the channel, because ultimately when we've gone to calculate risk, we've calculated basically in each 100-metre section of the channel. The third component of the calculation is probably the most critical, and this is related to, you have an incident, but what's the likelihood of vessel grounding? And so in this third component is where those human factors, which are particularly important. So these are actions of the shipmaster and ship crew, as well as the pilot and the tugs that are assisting the ship. And then finally, what's the consequence of grounding? So this could be the ship can be rapidly refloated either with tug or tide assistance, or what's the probability that the hull may actually fail as a result of being exposed over a large tide range cycle. And then once the consequence is defined, how long may that channel closure actually occur. So the original calculation had a period of hours, days to months, but with that incident escalation of the hull failure, you really end up with it being dominated into two categories of the ship is either going to be refloated very rapidly with a combination of the tide and tug assistance, or it's going to result in closure of the channel for many months. And then right through, and particularly over the last 5 years, we've followed a continuous improvement process where we've continually examined key risk drivers and then gone through a process of analysing, with actual data, how those drivers impact on the risk at the port, look at, how we can, do analysis and prediction of how those factors assess risk and how they could be mitigated, and then going through that process of on-water verification, which is a particularly unique component of the work that we've done at Port Hedland. Now, in terms of how risk has actually been mitigated, so as I mentioned in the opening slides, the port is an enormous economic asset for Australia. So it's over $50 billion US of trade is exported each year. And then over the last 8 years, the investment to mitigate channel blockage risk has been substantial. So over $300 million US has been invested specifically in pure risk mitigation for the port. There has been 2 major investments with respect to tugs, which so BHP implemented a $240 million escort tug project. There's another towage operator at Port Hedland as well that invested approximately $200 million in escort towage. And then for the outer part of the channel where escort towage was not had a relatively low risk reward benefit, we actually went about a process of channel modification to basically eliminate the risk of channel blockage in that outer section of the channel, where the cost of providing extended escort towage was extremely significant. So that was the $100 million channel modification project that has been completed to widen the channel. So essentially the channel blockage cannot occur. So some of the insights from the process and the studies we've completed at Port Hedland. So as I mentioned earlier, there might be a triggering mechanical or electrical system failure on board the ship. And despite a lot of attention being paid in the wider marine industry, as well as specifically for ships visiting Port Hedland, the rate of root cause, if you like, the underlying rate of mechanical or electrical failures for engine and steering related systems has actually been remarkably consistent. There's been changes in drivers and the root cause of those system failures over the last 10 to 15 years. But when you break it down into almost like a per ship probability of a major mechanical or electrical failure, that rate hasn't actually changed very much, which has meant that this is reducing the risk potential from if you like these root cause has a has had a relatively low effectiveness, which is why we've had to pursue other mitigations. Human factors is probably the most key incident, is the key driver for turning a potential incident into an actual impact with the channel margin or a vessel grounding. And it's really actually those human factors that lead to the escalation of a ship going off course and not being able to be corrected within that very short time frame of 1 to 2 minutes before a collision would occur or a grounding would occur. So the escort towage has been the key component, has been the key investment undertaken at the port to mitigate channel blockage risk. But a key thing to understand is that the escort towage is really only one component in the risk control framework or the risk control measures that have been implemented, because it's that combination of you can have the escort capable tug, but without the right process and without the control and bridge resource management, so without the right practices and procedures being implemented, it can have a relatively low effectiveness factor. So training and introducing of piloting controls and strategies that can utilize the escort towage effectively is absolutely critical to what is the risk control system that is operating in Port Hedland at the moment. And then finally, continuous improvement and always reassessing risk drivers has been absolutely critical as we've had to revisit the risk assessment process a number of times over the last 10 years. I'll just quickly touch on, some of you may be aware of a similar major bridge collapse which occurred in Australia in the 1970s. So this occurred in Tasmania in 1975. A lot of the same methods have actually been used by my team to verify the current risk of the replacement bridge that occurred there. So the bridge was repaired and replaced, and we've used the same risk assessment framework to verify the effectiveness of towage, and also understand what the likelihood of a collision there at the Tasman Bridge in Tasmania. And then finally, I'll include this with the slides. This is an example of the conceptual risk framework based on the model that we developed at Port Hedland, but looking at it in the bridge elision context. We're starting from those root causes of the likelihood of a failure on board the ship, and then working through the process of how is it transiting the channel, what are those human factors that might affect the actual end outcome, and then through the potential range of impacts that could occur from relatively minor outcomes right through to the most severe catastrophic collapse, and then to be able to actually define that in an economic analysis framework to trade off the cost benefit of risk mitigation options versus the actual total risk that's being incurred. So I know that it's gone a little bit over time there, but thanks for everyone's.
Thank you, David. There are two questions that are on the board. First one is, what is the length of the channel from the port to the sea? That was earlier on in your presentation.
So sorry, the length of the channel?
From the port to the sea.
Yeah, so it's 22 nautical miles in total. So it takes about 3.5 hours to transit from the port to open water.
Okay, and the last question is, So given that the bridges are getting older in the US and probably around the world as well, are there any guidelines or standards that the US should follow to check their bridges for elisions on a regular basis? Do you have an opinion on of that?
Well, that's probably that's not my necessarily area of expertise.
Okay.
But what I would comment there is that that's I guess the continuous assessment and needing to revisit the risk assessment outcome, or the risk assessment calculation, because in that context the capacity of bridges to withstand the collision changes over time. So whilst everything else might be the same, the risk can actually increase over time, despite the fact the traffic's the same, and economic value may not have changed. So I think that just highlights that example.
Great, thank you very much, David. And no, all yours. I think we're going to transition then to the panel discussion.
Yeah, great. Thank you very much for the presentation, David. Please, all panelists, stay online for panel discussion. I would like to invite Dr. Alampalli back for the panel discussion. Dr. Alampalli, you have seen him earlier. He's currently a distinguished member of ASC. He has been at the New York State for more than 30 years, managing the safety of bridges. And he has been honored with numerous prestigious awards from ASC, and others. And he's currently chair of the IABMS USA. And one thing is for sure about Dr. Alampalli is that although he has been in the government service, but his publication record, some of us in the academics, we have to compete with him for the journal and publication record. So very dedicated researcher, engineer, practitioner. Currently with the Stantec. So Dr. Alampalli would like to start the panel discussion. Please lead, and let's, if we have some questions from earlier, and then we can get more questions from the audience. Thank you.
Thank you, everyone. All of you we had some great presentations. I'm glad to see that still there are 400 people online. So if any of you have in the audience, you have any questions, keep them general and please post them in the Q&A, and we'll try to get to them as soon as possible. First, I would like, there are a lot of questions in the beginning of the chart on how do they get the slides and videos. I just want to answer that first. Professor Anil Agrawal is going to email all the attendees with that information. If we all the presentations where presenters have given permission for him to share will be shared there along with the video.
Yes, we plan to upload the video. I'll be talking to the contributors about the video part. So, on our UTRC webpage, where the schedule appears, will upload the video. It will take some time, but it will be there. And then on the website, we will again request people to solicit feedback. If they have some more feedback after watching the video, they can certainly give more feedback, and we'll be monitoring and looking at those feedback.
Again, ship collision design is not my area, but I learned a lot today. Let's start with, I made some general questions based on all the questions we got so far. Let me start first thing about resources. Something I haven't had is, if I am new or if I'm an owner, where can I find information on how to estimate risk and mitigation measures associated with ship collision, shipping impact? Like, where can I get some training and more information? I'll start with Preben.
Okay. Could you please repeat your question?
Let's say, where can one get more resources and training aspects when it comes to risk assessment and design and other aspects of ship collision?
Well, of course, the YAPSA has its green book. That's a good start, actually, I think. And of course, a new one will be available in some years, because I know that Albrecht Lenz has been charged with making a new guideline. And of course, you have to look also at what Mr. Knott told us, about this work which has been done in US in connection with the ASTO. That's probably also going to give you a lot of insight. And of course, then on more special things, there are papers in the open which you can go and study concerning the probability and concerning impact forces and things like that. So there's a lot of scattered information.
Any other panelists quickly would like to chime in?
I would just like to echo the comment that Mike Knott made earlier about the value of the guide specification. What's in the LRFD specification is much distilled, and there's a tremendous amount of valuable information in the full guide specification.
Okay, thank you. I have another general question. What technologies are out there to reduce the risk of events such as one we saw in Maryland? We really did not, spoke more about design, analysis, risk assessment. We really did not talk about technologies. Well, Sharif, do you want to start?
Well, I think, and we saw several presentations today about this. The use of simulation has advanced to the point where I think it is within the capabilities of many engineers. Companies call it democratization of simulation technology. And I think this is where we should be going next. We're talking about a bridge that costs multiple $billion that affects the livelihood of millions of people and an economy worth billions. So why wouldn't we deploy our best technology to assess the capabilities of how we protect it and how the ship and the bridge would actually behave under these conditions? I think everything is in place to do that, and I think the answer is in simulation.
Anyone else would like to chime in?
I really think that one of the problems is that we're talking about very, very low probabilities here. And that is also, for instance, as Mr. Knott told us, that from AIS, you can probably not get all these outliers. We are talking about something which happens every 10 to the 10,000 years or something like that. And that's difficult to simulate, and we cannot get data from AIS to all that. So for that reason, I should also maybe have mentioned this. You have the number of vessels, the majority of the vessels. You can get their distribution and look and calculate the probability that they collide with a pier, for instance. But there will always be some outliers which we cannot catch with these distributions, for instance, a log-normal distribution or the Gaussian distribution. So what the bridges I've been involved with, there we always assume a certain percentage of the traffic is spread all over the bridge width, so that, because otherwise we will have some bridge piers and bridge girder which can be made of paper, and we'll have zero risk. But we have a risk there because we will have some rock vessels going completely outside. So we have to do a lot of judgments, and I'm a little bit worried about trying to simulate everything, because I'm not sure it's possible with these very small probabilities.
Well, I would just like to say that this really small possibility has materialized, and 1 in 100,000 year event coming true with the Baltimore Bridge, to me, is something, it seemed unthinkable when the provisions were being written, and as complex as they are, and the way they mix all these different probabilities together to give you a number, in my opinion, that is not very meaningful. And I feel that for critical structures, just as we are designing a spaceship and all the costs attributed to that, we use the best technology we have, or an airplane. Why wouldn't we do that for some of our iconic bridges? There are not that many. The US has probably, a couple of hundred such bridges, and each of them is worth, as I mentioned, billions. I think we should be using this for such iconic structures.
Let me ask Ted to jump in, because he's a practitioner. He has worked with a lot of devotees as a consultant. Ted,
so I think so that's maybe two thoughts. One is that with deterministic evaluations, as Dr. El-Tawil is saying, this, yes, is the most capability what we have. I think the downside is we really have a probabilistic problem, right? So if we're using deterministic analyses to get our arms around a probabilistic problem, that represents challenges. So I just go back to the work both of Gary Consolazio and Dr. Peterson to try to come up with formulations which at least give us more simple abilities to do many more simulations, if you will, or to evaluate risk in a more broad way. So let's say this, I'm concerned about a few deterministic analyses against what a probabilistic problem what we have. And so I do think what Dr. Peterson mentioned is also essential. We have some baseline level of risk, what we have to design bridges for. And I think this is also something that gets a bit overlooked, but there should be some minimum threshold, I think, so we don't have circumstances where we have piers with very little vessel impact resisting capability. This is also something I think we could think about is a baseline level. And we, in some sense, have that, particularly in inland waterways where we have the flood condition with an empty barge. And so, but I think there's arguments to be made that we need to think about this as not doing necessarily a few simulations, but to really build on the work that Dr. Consolazio has developed, really, which is having the simulations feed into a methodology and to be able to apply that methodology more broadly.
Yeah, this is Mike. So it's a few comments. One is that I think the way forward is the first solution should not be to design the bridge to withstand an impact for large ships. We need to be looking at longer spans over the waterway. And so in the guide specification, there was a section on planning for new bridges, and it suggested that as a minimum, new bridges should be 2 to 3 times the length overall of the design vessel or largest ship in the waterway. So a 1,200-foot long ship, using that criteria, should be a 2,400 to 3,600-foot main span. This puts the bridge piers often in shallower waters where a larger ship can't even get to it. And so overseas, in Asia and elsewhere, it's quite common to see 3,000, 4,000-foot span bridges. And in the US, it seems we keep wanting to put our bridge piers close to a channel. So if it's a 1,000-foot channel, we'll have a 1,500-foot main span. Well, then you've got to design those piers, in my opinion, not to withstand an impact, but you got to put dolphins, islands, something to protect them from collision to begin with.
So Mike, I had a question. So, sorry, what you said just now that, if we increase the span, Srini, can I ask this one?
Yeah, please go ahead, because that's why actually it leads into a question we had. Somebody asked Abdullah who asked us.
So my question was that if you consider 2 options, option 1 is you have much longer span that you go into the shallower water, and option 2 is you keep the span but build a rock island or stronger protection system so ships will not go and hit the pier. So will building much longer span, will it increase the cost much more significantly? I mean, I have this question to you, Mike and Ted, both, that making much longer span just to put the footing in the shallow water.
Yeah, in my experience, a longer span offsets the cost of a longer span is less than the cost of a shorter span with expensive pier protection systems around it, such as dolphins and islands.
Okay.
And so a longer span is almost always a less expensive overall alternative.
So based on your experience, has there been, can you give me a threshold, where it makes more cost beneficial to have a longer span?
Well, I'll talk briefly about the Skyway Bridge in Florida. A new bridge replaced the existing bridge. It has a 1,200-foot span. The new bridge cost approximately $100 million back in the late 80s. the protection system for that bridge cost about $60 million to protect the 1,200 foot main span. So they invested about $160 million for the bridge replacement. Well, for $120 million, you could have probably at that time put a 3,000 foot main span, and the main piers would have been in shallower waters. So that's just a real world example where if you consider the cost of protection with the cost of the bridge development, it will usually drive you to longer spans.
So maybe I jump in here. So I think what's clear is in terms of long span bridge engineering, there's not a lot of linearity to costing, and the additional cost of much longer spans can often be prohibitive. So the challenge, I think, when you get above about 1,000 meters is that you're in circumstances where you're at the limit of cable stayed bridge technology, you're headed towards suspension bridges. If you're suspension bridges and you have weak soils and you have very expensive anchorages, you really go from something where you can have a relationship where the incremental cost is relatively small to where the incremental cost can be quite a bit larger. And so I think these are, it's really, I think, hard to generalize, but I would say such an analysis where you look at the cost of protection versus the cost of span length, I think this makes perfect sense. And then, you know, the challenge we have in front of us is obviously vessels are getting larger. Yeah, so only using LOA or LPP, a vessel length as a measure of this is also challenging. I think this question about risk comes back front and center, and I think this is also represents a challenge. For most of us, I think we also are in circumstances where we're replacing bridges and not building new bridges. I think if we were to think about maybe my US practice, it's 1 out of 10 is a new crossing. So 9 times out of 10, we're replacing an older crossing. And this is one that also represents different challenges. You have established navigational criteria or an established navigational channel. And it's hard to make the argument. I think what Mike Knott said about the Coast Guard's role in all of this is an interesting point. You know, they're really, especially when you have existing channels, the tendency to go much larger to reduce vessel risk is not something we generally see, but perhaps we'll see it more in the future.
Well, there's a comment here on Ben Bierman on that saying that the new design build probably, you know, there's an option to look at, you know, longer spans as a cost-effective saver, as a, you know, value proposition probably in the future. I just have one more question in this line of thought, and then we'll go in different directions slightly. I believe David mentioned about climate change. How do you guys think the climate change and coupled with all these new increasing loads and all is going to affect how we think about you know, building these bridges for the vessel impact? David, do you want to answer that question?
Yeah, thank you. Well, I think probably the key one is rising sea levels and how that actually changes, because that can have quite big impacts on the probability and also the, you know, if you like, the point of collision and impact on a bridge pier. So yeah, certainly when you're looking at things over a design life, you know, yeah, I would say, yeah, sea level rise would be a key factor in the assessment and calculation of risk.
Any quick comments from others before we go in a different direction?
Yeah, this is Mike Knott. So we typically include, as we increase our vessel fleet to the midpoint of the bridge, we typically also do a sea level rise prediction to the midlife of the bridge and use that as the baseline for establishing water depths.
Okay, thank you.
And to reduce the effect of climate change, I think also we could say that the ships are not getting smaller because the large vessels, they are much more fuel efficient than the smaller vessels. Of course, we'll see new fuel systems, ammonia and methane and ammonia. That we'll see, but that will not change that will not change the ship structure as such. It'll just be the engine room and some tanks. But if you want to reduce the CO2 emission from vessels, then you need a larger vessels.
So I'll just move on slightly to different. We spoke quite a bit about direct peer impact, and we haven't really spoken a lot about barriers and other aspects of it here. So there's a question from Mohit Soni that what are the possibilities of developing the standard barrier shape to protect the pier by deflecting the ship away from the pier? He quotes something similar to pier protection barrier in Florida. Anyone want to take that?
Yeah, Mike not here. So yeah, so in my opinion, the best way to protect a bridge is to put something in front of the pier that deflects the vessel away from it. And so a protection system that can deflect the vessel is much more effective than a protection system that has to absorb the impact fully. A large amount of the collision energy is absorbed if we can get the hydrodynamic mass of the vessel as it's being forced to turn or move. That's a great energy absorber rather than the structure itself. So these days, large diameter dolphins, which are sacrificial structures made to collapse and move about half their diameter. So a 100-foot diameter cell will, top of it, move about 50 feet to absorb the energy. Protection islands, they're environmentally difficult to implement in US waterways, but where they can be implemented, they are considered the best types of protection. And then there's pile-supported pier protection structures that can be placed in front of the pier to also try to redirect the vessel away from a collision with the pier.
Before someone else goes, I just want your thought on a question from John Andrews. What about underwater structures that can deflect the vessel? Are there any?
There are. In fact, islands don't have to be islands that come up above the water. Islands can be underwater to engage the bow of the draft of the ship and to either withstand a grounding or to redirect it. And so in some projects, we have recommended island protections where the top of the islands are underwater.
Thank you. Anyone else on the same topic?
And one, I would mention, I would really support what Dr. Knott, Mr. Knott says, but you have to look into what type of the slope of these islands, because as we saw before, a bulk carrier or tanker which grounds on an island, it should not break, because then you will have an environmental disaster. So you have to adjust the slope such that you can keep the hull intact. That's an important design criterion for these protective islands.
Any other comments before we can move on?
Yeah, I was just going to say, Mike, you want to mention something about, because I think the initial question maybe had something to do with like a cable arrest type system as well, which those can be utilized, but require long distances to stop a vessel of any size.
Yeah, the AASHTO code has a discussion of cable capture systems, and they have been considered. They tend to be not very practical for different reasons. Some bow shapes can ride over cables. Cables over the long term, particularly we're looking at a 100-year lifetime for a bridge, tend to corrode, disintegrate. And so cable capture systems have been looked at, particularly in extremely deep waters where you have, like across the Straits of Gibraltar, 500 feet or something. But in shallower waters where we're in, 50 feet or less water depths, structural alternatives, in my opinion, are better than cable capture types of systems.
We haven't really heard from Wei Fan. Can you mention anything from your experience in China on this topic?
Yes, actually, it's just like a cable, the protection systems has been used in some of the bridge is in China, just like of the bridge is crossing the like of the nearly the crossing the sea. It's like Zhejiang province, and some here use this just like cable, the protective systems like that. That one is used for just like it's not non-linear. Non-linear is the not that is not the non-navigations channels like that. Yeah, in this case, use this case.
There's a question from anonymous attendee on this area. What about protection for vessel superstructure collisions? We spoke mostly about pier protection. What about the superstructure protection, like what happened in, for example, Maryland?
This is Mike Knott again. So superstructure collisions can definitely be considered, and there are some guidelines in the code for deckhouse forces. We recently completed a study in Canada where we looked at an arch type bridge, which subject to mast and deckhouse collisions, that we developed with some assistance from others, developed some equations representing mast collisions and funnel collisions applied to the curve shape of the superstructure as it was moving back toward the waterline. Certainly complicates the analysis. So rather than maybe hundreds of pages in the risk analysis Excel spreadsheet, we wound up with thousands of pages for every little element of the truss bridge. But it can be done. I think for existing bridges, it can be done. But I think the lesson learned is for new bridges, don't build arch structures.
Okay. So in a similar fashion, there's another question here about, I think David mentioned, for example, having a pilot or a tugboat. Wouldn't it be more cost efficient to have a assisted pass under major bridges using a tugboat, for example? Should we be going that direction? Is it cost efficient rather?
Well, I think it maybe from an overall cost benefit, it could well be more effective. I guess that the challenge there is around, who pays for the cost and who has the responsibility. That's probably a bigger issue. The example that I presented there for Port Hedland was unique in terms of, that was a single system that was, under the control of one port authority to work out with the people who operated at the port what was the most cost-effective way to mitigate risk. But I guess that, particularly from what Michael presented, you've got Coast Guard requirements for navigation versus, the transport requirements for a bridge. I think that's probably where there might be differences in responsibilities and who bears the cost.
Any other comments before we want to jump into a little bit of design analysis side?
Yeah, Mike Knott here. I guess the AASHTO guide specification had 3 methods for designing the bridge for vessel collision. The method 3 was a benefit cost analysis accompanied with the bridge risk analysis. It was recognized that there are situations where you could spend an extremely exorbitant amount of money for very little improvement in the risk. And so combining the benefit cost analysis with the risk analysis was a way of saying, at what point do you have to stop spending money? Because these are very expensive structures. And so that's a tool that has not been used too often in the industry, but I think it's something that moving forward, particularly with the cost of protection systems being in the many hundreds of millions of dollars sometimes for an individual bridge, that we might consider using more often.
If there are no comments on that, I would like to jump a little bit to design and analysis side of it. I know Gary mentioned the differences between static and dynamic analysis, and he elaborated a little bit more on that. And I know Sharif also touched on that a little bit. So we also have several questions on the geotechnical side of it. So I'd like to know, maybe someone can elaborate more on differences between dynamic and static analysis, and also the expertise required versus, given these dynamic analysis and simulation cost a lot of money, is there really a benefit cost for most bridges? And how do the geotechnical considerations go in all these, complicated analyses?
Well, I guess in terms of from a dynamic standpoint, I guess it comes down to what type of dynamic analysis you're talking about. So we've talked today about high resolution, very high fidelity finite element modeling, and then simplified modeling. I think the level of expertise that's required for LS-DYNA type simulations is, perhaps, it's going to exist in some scenarios, but not others. You're not necessarily going to have the expertise to carry out that kind of a simulation in certain offices. And so the simplified approach is where some of the complexity of the impact is baked into simplified representations, I think has benefit and is within the reach of more practicing engineers maybe than are capable of carrying out an LS-DYNA type simulation.
We'd like to hear from Sharif and Ted a little bit on that too.
So for the small barges that we saw in Gary's simulations, it seemed that the response is a very short duration, which could be comparable to the frequency of vibration, to the frequency of the dynamic frequency of the bridges with which it's impacting. And so for those, dynamic analysis might make sense. For the larger structures we've worked on where the ship is also large, we've seen that the duration of the applied load, and I think Professor Peterson mentioned that as well, and others too, the duration is long enough that the peak forces act for such a long period of time with respect to the period of the structure that it makes sense to use that as the dynamic, as the static force. And so it's a case-by-case situation for stiff bridges that are impacted by low weight vessels. I think you might want to consider dynamic effects. Otherwise, they're probably not important.
So I would just offer that for usually for a large bridge, you have quite a sophisticated model of the bridge itself. And I think what Gary was suggesting is to apply, a simplified crush model to a complex bridge model. And this, in my view, has a lot of value. And I would say that when we look at any sort of impact event, and the one that I'm most familiar with is cable loss, anytime we want to do these as equivalent static loads, we just get very different results. Let's say in our practice, we do everything dynamically that's associated with an impact. Even on a large scale structure, the statics, the equivalent static loads just don't represent behavior. And I thought Gary did a nice job of describing just the inertial response of the structure and how that matters in the overall behavior. So I would say, if you were to ask me, I'm a fan of doing the dynamics, but simplifying the crush load side of because I think this is something we don't know, right? We're looking at thousands of ship passages of hundreds of different types of ships, and we're trying to then calculate some sort of generalized behavior against some average ship. It seems to me like we would be much better off doing more simplified ship simulations to understand global structural behavior. And we're really, as an industry, set up to do that. I think for us, the global model of a large bridge will often be dynamic anyway, whether it's for seismic or for wind or for cable loss. So I think these are the sorts of things that allow us to do the dynamics. And I think, and having the load represented as an equivalent dynamic load that can be applied as a force time history, I think there's a lot of value to that in terms of getting to safer structures.
Sharif, do you want to comment anything?
I've been also experienced that if you can allow, for instance, a gravity-supported pier, if you can allow, say, 1 meter displacement,
Displacement, yeah.
right, you can take a lot of energy.
Oh, yeah.
If you take the dynamic analysis. So you should definitely do the dynamic analysis of the bridge and taking into account the mass, of course, of the vessel and a load deflection curve, which is representative for that vessel. So I really recommend that you do that, because every bridge builder has a good model of his bridge.
One other comment I'd like to just make. I didn't get into this today, but one of the benefits of using simplified modeling is it allows you to do probabilistic simulations in some cases where you can probabilistically investigate the effect of different situations, whether that's impact angles, whether that's structural characteristics, soil conditions, or so forth. And having simplified methods facilitates things like Monte Carlo simulation, whereas relying solely on very complex models, it's much more difficult to achieve those kinds of simulations.
Well, to continue on this line, I would also say that if you have these oblique impacts, then of course you should take into account that the vessel, can slide, and of course, dependent on the coefficient of friction between the vessel and the concrete, then of course you can have different forces, transverse forces, but you should take into account the swaying of the vessel and its added mass from the water, because then you reduce the impact to the pier quite considerably.
I know we are approaching almost 3:25 now. Anil, you want me to continue, or you want sort of?
If we still have questions, then we can. This is a great opportunity to have discussion. So I think we had planned till 3:30, and we are late. We're late by 10 minutes, so we can go for 10-15 minutes, and then we'll close it.
We don't have a lot of questions online. I just have couple other questions. Sharif mentioned about robustness and redundancy in his presentation. He highlighted them. So whenever you are designing these kind of structures, you always have to look at multi-hazard design, definitely. So what are the other hazards which are complementary here and which are contradictory, which we should consider, and how do we optimize them along with vehicle impact when we are doing these analysis and everything else? Sharif, you want to start?
Well, the other hazards, of course, are natural hazards, and these pertain to hurricanes, for example, in coastal areas, perhaps more so in seismic on the other coast, in the West Coast. So they generate different types of demands, but in general, robustness is just being about strong. And one of the criticisms I have regarding, and that's why I put it in the presentation, regarding the current guidelines, they actually put the force as H over P, the capacity over the demand, ranging from 0 to 1. By putting in 0, you're implying you could have a piece of paper supporting a bridge. Obviously, that's not what is meant. But I feel as a structural engineer that you have to have a minimum strength. And by doing that, and for a large bridge, this strength should be large as well. You're actually eliminating certain kinds of systems that would lead to what happened, for example, in Baltimore. So that is what I was trying to imply in my presentation, the robustness aspect of it.
Any other comment? Anil, you have any comment?
Maybe the one big one, what we have to contend with is the combination of scour and vessel impact, right? This is one that we often see and drives particular demands that I think are in some circumstances really drive design of the foundation system. So the joint probability of and it's typically the short-term scour event in combination with vessel impact. That's something that I think it's been studied some in extreme event load combinations. But I think that's another area for some some opportunities, because I think, let's say the scour event and the combination of vessel impact with the scour event, these are very low likelihood events in combination and could be studied further.
Yeah, so this is Mike. So in my experience, extreme events will control the design of long span bridges. It's either going to be a large earthquake force or a large vessel collision force associated with a scour event. I wanted to make one comment on a couple things said earlier today about the AASHTO code and the simplified equation based on deadweight tonnage and velocity. The deadweight tonnage, so to be real simplified about it, container ships have pointy bows, as do freighters. Typically, bulk carriers and tankers tend to have rather blunt bows. And certainly they have a softer bow when they're traveling ballasted than when they're loaded with more energy. But in the US waters, empty tankers and bulk carriers bring on water ballast to bring their bows down into the water for maneuverability and steerability issues. And so there are ballast tanks in the front of the ship that are filled full of water. And Professor Weissan suggests that his research indicated that though the impact from an empty tanker or bulk carrier was less than a loaded carrier, when you put water in the bow of the ship, it stiffened the bow, similar to ice strengthening, and that the water ballast in the bow made the bow stronger. And so the impact forces were about the same based on his research from a loaded bulk carrier with no ballast in the forepeak of the ship versus a ballasted bulk carrier with water in the bow of the ship that was strengthened. And so that's why at the end of the day in AASHTO, we didn't differentiate between loaded and ballasted.
Now that we are almost 3:30, I want all panelists to answer this question, maybe 2-3 sentences max. Now that we are here, where do we go from here? Can you identify 1 or 2 topics where research or practice or even the policy or as well as the communication between vehicles, from the freight or vehicle side of impact, the boat side of it, as well as from bridge engineers. I'll start with
Srini, I'd like to start because I'm going to say something controversial. I'm curious about.
Okay, go ahead.
From my colleagues.
I don't want this becoming a 1-hour discussion, Sharif. So all of you can answer, it would be great.
Yeah, it's related to what you mentioned. I was surprised by the resistance to use simulation models and the focus on simplified models. So simplified models, we also call them reduced order models. They're calibrated to more advanced models, and they are limited by the calibration process. So I'm just surprised that as an industry, we would limit ourselves in terms of what we are capable of doing. The roadside hardware industry for all around the US is now using these advanced models for qualifying new roadside hardware. So why wouldn't we do that?
I guess one response to that would be that roadside safety hardware has to be crash tested to prove performance, whereas bridges are not.
Well, Gary, what is happening lately, more roadside safety industry is moving more towards simulation. So we have last 2-3 years, we have done testing of, not directly, but the agency have done testing of roadside hardware, and we have done the simulation.
I would say they're different in a way, Sharif. Simulations for vehicular impact are standardized around very specific vehicles. It's a different problem. We have the problem of this wide array of vessels, and one wonders, and I think Mike Knott mentioned this, or maybe it was I think it was Mike. The variability of cruise shape, the shape of the bow for cruise ships is just mind-boggling. In the last 10 years, as near as I can tell, from vessels that are transiting under Verrazano, there's every measure of cruise ship bow shape. And while there's some standardization across tankers and container ships, I say there seems to me almost no standardization in cruise ship bows, and yet these represent perhaps very different circumstances. So where I get stuck is if we're too deterministic, we have one complex vessel impact simulation for one bow shape. What have we really learned about the overall risk? And that's where I like these broader based sensibilities and doing more, I would say, simplification only from the perspective that we can look at more scenarios, not less. Said that way. So I'm with you that we should do sophisticated things, but I think we need to do many scenarios.
What if we had 10 different models representing 10 different classes of ships? Would that take care of it?
Yeah, although you would say even one class of ship, if you just looked at cruise ships and you looked at the variability of bow shapes in cruise ships, I think it would curl your eyebrows.
Okay, I think we need to, as I said, maybe we should make all the ships have one bow shape, and that will solve both of your. So,
Yeah.
I would like to go one individually and ask same question what I asked. Give me one topic where I think we should, go from here in advance type of thing. It could be policy or design or communication side of it. I'll start with the Preben. Just 10 seconds each.
Yeah, the sound faded a little bit for me. So could you please repeat your question?
Give me one topic where we should be, working much further from here. It could be
I really think that the largest uncertainty we have here is this probabilistic approach to find the design vessels. There are so many uncertain factors there. So if you really want to improve our models, that will really be where we could do the most to get a better idea about the probability of collisions against the individual peers, and from this then extract design ships, which we can then use to do simulations against the bridge structure. But I think that the structural part of it, we have much better hold of that than we have the identification of the ships which collide with the bridge. I think that's the largest uncertainty we have.
I just have one comment about what Ted said earlier. So yes, roadside hardware, we have one track model, but if you look at in the real life, the models of the truck, and we have studied this, I have studied this for MTA, that if you look at the models of the trucks and the type of load carry and the height of the bed of the truck, which controls the impact on these roadside barriers a lot. So they're very wide variability there. The engine block.
It's not that. Yeah, it's not.
Anil, I think we need to stop that. We can do it later. Okay. Let me go back to Salvatore. Salvatore, can you answer my question?
Is he here?
He's not here. Maybe he left. Okay. V.
I think he has left here.
Yeah, left too. Okay. I'll go to Ted.
Yeah, I'm in total agreement with Dr. Peterson. I think we really should focus on the probability side of impact, and I really do feel that AIS data and extreme value theory is ready for us to look much more carefully than what our empirical relationships have had in the past. And I'm very confident that with big data sets, yes, maybe for one crossing, you don't have enough data, but we have hundreds of crossings just in US data. And Gary, if people are interested, I recommend to you Gary's work on looking at this statewide for Florida DOT, and even looking at probability of aberrancy and tackling the hardest problem, which for me is barges. And he's done quite an extensive bit of work on that and has made progress. And a lot of that has been predicated on AIS data. So Gary, I hand it over to you. Do you disagree with any of that?
Yeah,
Go ahead, Gary.
Yeah, I totally agree. I mean, I think on the topic of developing standardized procedures for probabilistically describing the vessel traffic and making use standardized procedures for making use of AIS data. As Ted just pointed out, we did do a study for the state of Florida where we looked at traffic around the state. State of Florida has a vessel pass point database that's used for designing vessels around the state, and we recently updated that. And we made heavy use of AIS data in that process, but perhaps developing standardized procedures that could be used by consulting firms in the or bridge owners in the process of developing the traffic characteristics, I think would be very helpful to the industry.
Sharif, nothing controversial. One topic.
Let's say, I think I don't want to go beyond that. I think the models that I had in mind in terms of simulation do not have to rise to the level of complexity that I think some of you understood. But having some models that could be used to push against dolphins, or some of the equipment that would be placed around bridges, and give you an idea. But it's better than nothing. Give you a really good guess about what the resistance of those would be is what I had in mind. This is what I would love to see sometime in the next few years.
Anil?
Well, I think where we go from now is one urgent thing that we have not done. And, if you look at the data, then all the ship impacts till now, more than 50% happened in the US. And I think there's a need to develop risk identification and management system that risk should be managed on a continuous basis, just like we manage risk for bridges by inspecting. Similar way, there should be a system where we evaluate, what is the risk of collapse. If you look at the cost of the bridge is nothing, $1.5 billion. The economic cost of that key bridge collapse is $15 to $20 billion. So it's not just the cost of the bridge or how much it costs to retrofit or put this protective measure. We are looking at the key bridge collapse overall going more than $20 billion. And even you have to put $50 or $60 million to protect it. It's not much, if you think what is happening. So the key thing is actually, from my side, identify the risk and develop a plan to manage the risk. And we have the tools to manage the risk. And if we do that in regular manner, we'll be able to prevent a lot of these accidents. I think Mike Winter wants to say something.
Yeah, I wanted to weigh in real quick as well. I think where do we head to now or next for me is I really think that we should maybe look at updating the guide specification and or the code. The work that Mike Knott did, the original guide specification, like Mike Knott mentioned, is almost 35 years old. And the work that went into that guide specification is from the 70s and 80s. So we're pushing near 50 years old.
Right.
Unfortunately,
I agree with that, yes.
Like Mike mentioned, the guide specification has been archived by AASHTO. I don't even know if you can readily available to get a copy of it. But and it was unfortunate that the guide specification at over 200 pages was reduced to 20 pages in the code. It did eliminate a lot of the background. My fear being the next generation, I am in my early 50s, but my fear being the next generation is that if we were to update the code, we've already lost individuals that helped with the original code. While we still have the Mike Knotts available to help to provide insight on why the original code was developed, why, some of the background, some of the history, I think it needs to be done in the short term because of, we're eventually going to lose the Mike Knotts having that wealth of knowledge available there. And so, that's my biggest fear. I really do feel like we need to do, put the pressure on to the organizations to say, hey, this is an important, especially now with the recent tragic events, and even after the tragic events with there was the temporary shutdown of the Chesapeake Bay Bridge. There's been others. This is the opportunity to say, hey, we really need to get some of the best minds available out there to look at redoing this. There are new things that with the computer modeling, with the simulations, the AIS data. There's a lot of things available to us to make these better. And I think that's what we need to do is we need to take the code, which when it was originally introduced, it was a groundbreaking, it was the gold standard, still is the gold standard. It was a groundbreaking document. And so we need to take that and we need to advance it now into the 21st century. I'll step off my soapbox. Thank you, everyone.
Thank you. I think it was Michael Winter, right, who spoke now? Michael Winter, you have any comments?
Sorry, that was me. That
Oh, no,
was
sorry, Mikele,
just,
do you have any
you may
comments?
see if Mike- you may want to see if Mike Knott has any comments.
Okay, go ahead. Okay, you have any, Mikele, you want to say anything?
Yeah, thanks. I think there's been some great ideas today, and certainly I think the industry would be best served with some
Mike,
updates. I would say the guide specification and then that would lead into changes in the code itself. Probably. Certainly the work that Gary and the University of Florida has done is a big help on understanding barge impacts. That certainly should be updated. And with some of the information suggested today, the larger ship collision forces should also be looked at and possibly updated.
Okay, thank you. Mr. Winters, do you have any comments to add?
That was me earlier. I'm good.
Oh, the early, I had a little confused there. Okay, sorry. And I leave David.
I think David is gone. He's a little more.
Okay. So I know there's like Hong Fan and Qian hasn't said anything. Qian and Hong Fan, you want to say anything? Your opportunity now.
Chen, do you have any comment? You are a practicing engineer. Any idea? Anything you want to add? You still there? Chen?
Yeah, Professor, I'm here.
Okay.
You have any comments?
Yeah, I'm good. Yeah, the presentation and discussion are really good.
You have two devices. I think there's a feedback coming.
Yeah.
Yeah.
Okay. Maybe I'll go to Wang first. Wang, you have any comments?
Hong Fan?
Yeah, me. Yeah, I agree a lot. Yeah, a lot of as persons say. For me, I think is it's the best solution is try to avoid this accident to happen, and if not, so because in the United States we have so many existing bridges, so I think the protective structure is the best solution for these existing bridges. We have risk of vessel ship impact on the bridge. So if you do that, yes, that probably can prevent a lot of accidents, especially for some key bridges like what happened in Baltimore. And I think the analysis should be do that. And the cost of do this analysis actually it's our protective strategies is going to be low compared to what the accident brought us. So I think simulation and other is very good tools to help us to get understanding of the bridge behavior and such with impact. And but if we can do to better the predictive ways strategy to avoid these things happen, that was better. But I think there's just a lot of ways we should do that. It's one to try to avoid this. Maybe the first choice. The second thing is if something we cannot do it for a lot of existing bridges, you cannot do much. So we are trying to think about what we can do. So protect those things, and if not, especially for the key bridges, I think efforts should be spent on it, how to prevent this one. If not, what would bridge behavior under the under ship impact. Yeah, because we have so many existing old bridge was not designed for the such a ship impact. So especially for large ship. Yes,
thank
a lot
you.
of work.
Chen?
Yeah, hi, Professor. Yeah,
we can hear you much better now.
Okay, yeah. So actually, I have some insights I got from Dr. Ted Soli. Since we have a lot of data, AIS data in available, and based on the available data, we could develop some warning system to the bridges. Like we have a lot of overhead impact for the trucks, and there are a lot of research going on to develop warning system for the overhead impact for the trucks. So maybe we could develop some similar type of warning system for the bridges, for both the bridge owners and the ship operation authorities. So yeah. Thank you,
Chen. Again, thank you everyone for a great discussion. I know we can continue for a long time, but I think it's only 3:45. Probably time to wrap it up.
Yeah.
Thank you everyone. Anil, back to you.
Yeah. So this was really we want to thank first of all the panelists. Your time matters and outcome will be there, very good outcome of this workshop. We want to thank the audience, our volunteers. Really, a lot of work went into organizing the symposium, but we wanted to do this actually from the day one. Me and Sarif were talking that there was general sentiment among the people when the Dali hit that he could not do anything about it. That's such a large ship, the bridge will not survive for. And then I said, how can it be? You have always options to design something. So it's really great. We want to thank everybody. Great audience. We are going to work on the PDH and we'll contact you how to receive the PDH. We are going to take these video recordings. I'll be contacting each of you to get your permission, and each of the video recording will be on our center website where people can view further. And if somebody has more comments, we are always ready to get the comments. And starting from now, me and Sarif probably will be spending a lot of meetings to see what feedback we got to come out with the proceedings or some recommendations or something that will have a follow-up, symposium or a couple of hours of meeting, online Zoom meeting, where we'll talk about what really came out from this symposium. So with this, I want to close the symposium, and I want to really thank you all for participation, all the speakers, audience, and our support staff from the center, and my postdocs, Dr. Wang and Dr. Chen. Thank you very much.
Thank you.